Yeah, good morning. Welcome to the last lecture. So the final lecture of model checking is about the following. It's about bisimulation. So I'm going to explain what bisimulation is. I think most of you have probably already seen this in Malo. Is this correct? Yeah? Good. And the main result that we're going to see today is the following theorem. And that says that basically bisimulation, and actually the notion we are considering is sometimes called a strong bisimulation, because actually there is a whole zoo of notions of bisimulations. There are several variations of it. This coincides with CTL equivalence. Yeah. So that means if I have two states or even two transition systems which are CTL equivalent, then they are bisimilar, and the other way around. If they are strong bisimilar, they satisfy the same CTL formulas. Okay? And this coincides also with CTL star equivalence. And that's perhaps a little bit surprising. We have seen the logic CTL star, which contains LTL and CTL and is strictly more expressive than both of them. But the equivalence induced by this logic coincides with CTL equivalence. So if I have two states that I cannot distinguish by a CTL formula, then I can also not distinguish them by a CTL star formula. Well, that's maybe obvious to understand, but then the other way around. If I cannot distinguish two states by a CTL star formula, so there is no CTL storm formula that holds for one state, but not for the other, then it's also no CTL. And C, this is also equivalent to CTL without until equivalence. So even if I take CTL, I remove until, which means I remove box, I remove diamond. The only thing I have is next. Yeah? That's all. These three equivalents all coincide with strong bisimulation. Now I have to be a little bit more precise. This is all true for finitely branching transition systems. That means, intuitively speaking, any state, so the transition system itself may have countably infinite many states, right? But every state only can have finitely many direct successors. That's the point. Yeah? But if that's the case, then actually those four things all coincide. Good. Let's start by first arguing that trace equivalence does not fit well with CTL, which is something I think we have already mentioned before in one of the earlier lectures. So here is a counterexample, and it's a typical counterexample for distinguishing trace equivalence with bisimulation equivalence. Here you see that it has a trace gray, gray, red, and then for continuing red, and gray, gray, blue. This has the same set of traces, but the difference is that here is a state in the middle that has both a red successor and a blue successor, which is not present in the left one. Yeah? So they have the same traces, but if you now consider the CTL formula, there exists a next state which has both a red successor and a blue successor. That's a formula that holds in the right transition system but not in the left transition system. Yeah? So we have two trace equivalent transition systems, but we can distinguish them by CTL. So conclusion, trace equivalence is not compatible with CTL. Good. So what we are interested actually is, and that's the main reason also of this theorem, is this what is written down in the lower box. That is, what you would like to do is you would like to define something like an equivalence relation, such that if you take a transition system that satisfies a formula, if and only if that transition system under that equivalence relation satisfies the formula as well. Now, things in terms of a finite state automaton, this is the quotient, the minimal deterministic finite state automaton. Here the same thing, you have a transition system, and we're going to see under strong bisimulation. How do you get the quotient? You just group all equivalent states and you represent it by a single state. Yeah? Good. And the good thing about bisimulation is you can compute this quotient very efficiently. Good. So what we know is, about trace equivalences are things like this, that if I have the finite traces of T1 are included in the finite traces of T2, then we know that this preserves safety properties. Yeah? If T2 is safe, then T1 is safe as well, because it has less finite traces, and therefore there are no counterexamples. The same for infinite traces, but that means then for all LTL properties, if T2 satisfies an LTL formula, then T1 satisfies an LTL formula. None of the LT relations like trace inclusion, trace equivalence is compatible with CTL. That's what the previous example showed us. And what furthermore is important to take into account, that checking those LT relations, for instance, checking whether two transition systems exhibit the same set of traces, is p-space complete. So that's an intrinsically hard problem. For bisimulation, this can be done in polynomial time. Actually checking whether two finite transition systems are strongly bisimilar is p-time complete. Good. Now there are all variations. I'm going to skip this slide. This is also only there for completeness. So what are we going to do? We're going to look at bisimulation, which is defined. You can define it in several possible ways. But suppose I have two transition systems. The actions are not relevant. The only important thing is they have the same set of atomic propositions. Okay, so the same labelings. Good. And then the bisimulation requires that T1 and T2 mutually can simulate each other. So this is a definition, a bisimulation for the paired transition systems T1, T2. We look at relations that contains pairs of states. States in T1 are coupled to states in T2. So it's just a binary relation, but this binary relation, in order to be a bisimulation, has to fulfill the following properties. For any pair of states in the relation, we have a couple of properties. First, the two states that are related must be labeled the same. I hope that's something that is obvious, because if they're not labeled the same, it's easy to distinguish them by an atomic proposition. That's not what we want. The second condition says the following. For every direct successor of S1, and the best is to look at this picture. So suppose that S1 and S2 are in the relation, and S1 has a direct successor, S1 prime. Then, in order for being a bisimulation, it means that this picture implies that S2 has a direct successor, S2 prime, and this S2 prime is mimicking the direct successor of S1 by R. So basically what people sometimes call this is a co-inductive definition, because you are telling me for any pair of states in a relation, something has to hold for their successors, for S1 prime and S2 prime. And this also has to go in the other direction, because it's a bisimulation. That means for every S2 prime being a successor of S2, I think that's on the next line. So if S2 has a direct successor S2 prime, then S1 needs to be able to mimic this step by having a direct successor S1 prime, such that the two successors are related. Good. Now the only thing that is left is that we have to say something about the initial states of the transition systems, and that's the last condition. So basically this says for every initial state in the first transition system, there needs to be an initial state in the second one, such that they are related, and vice versa. For every initial state on the second one, there needs to be one in the initial one that are related. Good. Okay, such that it is fixed that we start basically in similar states. Good. So that's what defines when a bisimulation, when a relation of those pairs is a bisimulation. Yeah. So that's what we just have seen. And now we define the following relation. This is what they call a bisimulation equivalence. And this bisimulation equivalence is indicated by this trigle symbol, and this says T1 is bisimulation equivalent to T2 if and only if there exists a bisimulation relation, yeah, for T1 and T2. Yeah. So you can think about this as the union of all bisimulations on that pair of transition systems. Good. So I hope you understand the difference. There is a definition of when a relation is a bisimulation. So either a relation is it or it's not. And then we have a special kind of relation, namely this bisimulation equivalence, that says there must exist at least one bisimulation. Good. And that's the same. You can also lift this for states, but that's basically similar. Good. So let's look at a small example. Here there are two beverage machines. The atomic propositions are indicated by the colors. And the claim is that these two things are bisimilar. That's not difficult to see because basically what you see is that this whole picture is included here. This only option has an extra Coke option here on the left, and then go back to blue. Yeah? So what's the bisimulation relation? I mean, this state is related to that state. This gray state is related to this gray state. Basically, every equally colored state is related to every equally colored state. For instance, this Coke 1 can move to a blue state, but that can be mimicked by this one by going to a blue state, and vice versa. Good. Here is the example we have seen before. These two things were trace equivalent, but they are not bisimilar. What is the point? The point is that here is a state that has both a yellow and a green direct successor. In the left transition system, there is no gray state which has a direct yellow and a direct green successor. So how is this materialized? So we say they are not bisimilar because there does not exist a bisimulation relation. How can we fill this? Because there is no state in T1 that has both a successor labeled with this yellow and green. So there is no state on the left which can mimic the behavior of this state on the right. Yeah? Good. Any questions? No? Good. Okay. So we have seen that this is the important condition of a bisimulation, that if S1 has a direct successor S1 prime, then S2 must be able to mimic this and go to a successor which is related to the successor. And actually this can be lifted to paths, and those paths can be finite or infinite in the obvious way by an inductive argument. So suppose that we have S1 being related to S2 and assume R is a bisimulation relation. Yeah? And S1 has some kind of computation starting in S1. Good. Then this picture can be completed to this one. The first test, well, okay, if this one is related to that one has a successor, that this S2 must be able to mimic this, so S2 will be able to move to a state S21 which is related to S11. And now you can apply the same reasoning to those two states. So that means that actually because this one has a direct successor S12, that one needs to have a direct successor which is able to mimic this state. So you get this, and so forth. Yeah? So what does it mean? If I have two states which are bisimilar, if I take a computation starting from one of them, the other one is able to mimic this in a stepwise fashion. It is able to move to the next state while still being bisimilar to the successor of the other state. Yeah? Good. Immediate conclusion. Give me two states which are bisimilar. They exhibit the same traces. Yeah? Must be. Immediate consequence of this thing. So they satisfy the same LTL formulas. Good. So now I'm just focusing in on this bisimulation equivalence. Yeah? On the previous slide, this holds for any bisimulation relation. But what is specific about bisimulation equivalence is the following. First of all, it's an equivalence, which means it's reflexive, transitive, and symmetric. So how can you see this? So first of all, we need to guarantee that T is bisimilar to T. How do we have to prove this? Well, this means there needs to be a bisimulation relation that relates T to itself. Okay, how would that bisimulation relation look like? Well, just the identity. Yeah. So this is not so difficult, that if you just take the identity relation, you can easily check that this satisfies all the properties of being a bisimulation for T when you compare T with itself. It's also symmetry, so that is the obvious requirement. How do I prove this? Well, you start from assuming that T1 is bisimulation equivalent to T2, so there is a bisimulation relation R relating T1 to T2. Proof obligation, you have to find a bisimulation relation that is relating the opposite. How do you get this? You take the inverse of the relation. Yeah? So that's pretty easy. Similar transitivity. If you know that T1 and T2 are bisimilar and T2 is bisimilar to T3, then transitivity says T1 is bisimilar to T3. So how do you show this? Well, you have to show this relation. So you start from this relation, because there needs to be a bisimulation relation. You start with that relation, and then what you do is, in order to get the relation here, you take the composition of the two relations. And then you can prove again that this thing is there. So it's written down here. Suppose R1, 2 relates 1 and 2, 2, 3 relates 2 and 3, and now you simply build a relation that relates states in the first with the third transition system by saying, okay, there needs to be some kind of intermediate state S2, which is related via 1, 2 and to S3 with R2, 3. Now what you have to prove, this is a bisimulation, but that's pretty straightforward. So it's good to understand that not every bisimulation relation is an equivalence, but this one is. Yeah? Good. So here is an example. Question, are those two bisimilar? So what do we need to find? We need to find a bisimulation relation, and this is not the case. Why is it not the case? Well, what you see is that S1 can move to a blue state, yeah, but this would be able to mimic by S2, but S2 cannot move to a blue state. So that cannot be mimicked. So S1 and S2 are not bisimilar. What about these two? Well, you have to be a bit careful. So here you can move to those two yellow states, but those two yellow states are basically copies of this one. This blue state is a copy of the other blue state, and we have copied the red state twice. So this looks pretty okay. So in order to prove this, you have to find a bisimulation relation. The obvious thing is to pair those ones that are colored equally. Yeah? And of course, then you have to prove that all the properties hold, but that's obvious. For instance, if you look at U, U can move to S1. Can this be mimicked by Y? Yes, it can be mimicked by either going to here or going to there. And vice versa, this one can move, for instance, to S2 prime, but that can be mimicked by U by moving to S1. So that's in both directions, that's fulfilled. Good, some other examples, but that's not so much important. So bisimulation versus trace equivalence, I actually already mentioned this, that if two transition systems are bisimilar, then they exhibit the same traces. This was this lifting of the relation to paths, but not the other way around. That's the same example as we have seen before. This state has a direct successor, which is red and green. This one has not. The two are trace equivalent, but not bisimilar. Good. Now we have defined bisimulation equivalence as a relation that compares two transition systems. It's sometimes convenient to define it as a relation on a single transition system. Why is this? Well, basically, what we would like to have is a result as follows. Suppose I have a transition system. I need to check whether it satisfies a CTL state formula phi. I would like to have something like if and only if T, yeah, under bisimulation equivalence satisfies phi as well. Yeah, so what I would like to have is I would like to have a relation that is able to compare states in the same transition system, and we would also like to be able to compare states in these two, and that's the relation we just have seen. Then you have to show that actually there is a relationship between these two transition systems. Some people define it directly on a single transition system, but that's basically the same thing. So we defined it in the following way. We compare T1 and T2. But you can also relate it on the states of one single transition system, T. So then you say that S1 is bisimilar to S2 inside a single transition system if and only if the transition system that you obtain from this one by declaring S1 as an initial state is bisimilar to the transition system that you obtain from that one by declaring S2 to be the initial state. Good, and that means that that's equivalent that there exists a bisimulation relation for S1. So what you do is you compare TS1 with TS2, and then you can compare the two transition systems. Yeah, so it's very easy to change between the two perspectives. You compare two transition systems, or you compare states within a single transition system. Conceptually, that's not much of a big difference. Good, I'm going to skip this because I basically said this already. Now, we have seen already that this bisimulation equivalence is a special relation because it's an equivalence. But it's the following relation which makes it even more interesting. It's the coarsest bisimulation on T. Yeah. That means the following. For any bisimulation relation that you can find, yeah, this will always be finer than this one. Yeah? So that means that suppose I would like to, so intuitively speaking, this simply means that it yields the least number of equivalence classes. Yeah? So in terms of if you would like to do things like minimization, suppose this is huge. Yeah? This is 10 to the power, whatever, 26 states. Yeah? If I am able to minimize my transition system with respect to bisimulation, and if I'm able to prove that this holds, yeah, then thanks to the theorem we're going to see, they preserve the same CTL formula, so it makes sense then to do the model checking in this way. Yeah? And this one can be much smaller. How small can it be? Now, because this is the coarsest bisimulation, yeah, it's the smallest transition system that you can get, yeah, which still satisfies the same CTL formulas. You cannot make it smaller without violating, sacrificing the correctness. Yeah, that's what this theorem says. And that's why bisimulation equivalence is such a nice relationship. So it's the coarsest relation that satisfies all the constraints of a bisimulation relation. That's what this slide basically tells you. Good. I'm going to skip this because this is basically... Okay, so what's the aim now? The aim is now that we can define the bisimulation quotient. So that's pretty straightforward. We start with a transition system, and this transition system could be infinite, and we are interested in the bisimulation quotient. What's the idea? We're basically going to collapse bisimulation equivalent states. So how does it work formally? We're interested in the transition system modulo this bisimulation relation, and this is defined as follows. The state space is simply the set of equivalence classes under bisimulation. The equivalence classes, of course, in the original transition system. What is the set of initial states? You take the equivalence classes of the initial states of the original transition system. What is the labeling function? Well, the labeling function L prime of such a representative of this equivalence class is equal to the labeling of, well, you can pick any state of the equivalence class because one of the constraints in bisimulation says all states need to be equally labeled. So we know that all the states in this set are equally labeled, so you can pick any arbitrary one, and that means that this is well defined. I think that's written down here. And the transition relation is as follows. If there is a transition from S to S prime, then this induces a transition between the equivalence class of S and the equivalence class of S prime. Yeah? The actions are not relevant. I mentioned already before, the actions do not play any role. So if this would be some action alpha, you can rename it if you want. It doesn't really make that much of a difference. Good. Then the essential thing is you can prove now that T is strongly bisimilar to its quotient. How would you prove such a thing? Well, in order to prove that T is bisimulation equivalent to T thing, so we have to prove T is bisimilar to this thing. How would you proceed? Well, in order to prove this, we have to find a bisimulation relation R that's going to relate this transition system and that transition system, right? So how would that look like? Well, the obvious candidate is you're going to pair a state with its equivalence class. Yeah? So you're going to take the thing where you take S, and you take S, the equivalence class with respect to this, for all S in S. And it's not difficult to check that this is a bisimulation relation. So the obvious candidate here will work, and that shows this important result that T is bisimilar to T modulo bisimulation equivalence. Example, suppose that we have a couple of printers all running in parallel. So we have n printers in parallel. Every printer is just a two-state transition system. It's ready or it's printing. And we have atomic propositions that basically count the number of printers that are available. So either there's nothing available or all printers are available n. Then a transition system for the case that we have n equals 3 is a transition system that looks as follows. So we start in initial state, all printers are ready, indicated by this triple R. Then one of the printers can start printing. Either the first printer starts printing or the second one or the third. Then another one can start printing. For instance, from this state you can move there, or this printer is released and then you go back to the initial state and so forth. Good, so these are the atomic propositions. It's just counting the number of p's in a state, right? So all these states are pink because they all have 2 p's, so 2 printers are occupied. And the bisimulation quotient looks like this. So if I take this as the set of atomic propositions, so the only thing that I observe are the colors. Yeah. Then the bisimulation quotient is you just group all the states. So for instance, we take all the pink states. They are equivalent. So we represent them by a single equivalence class, which is represented here. We have here a transition from pink to yellow. So there is a transition here from pink to yellow. There is a transition from pink to green. So there is a transition from pink to green. And those are the only transitions which are there. So they're only the transitions in the quotient. Good. In general, this leads quite a couple of reductions because on the left-hand side we have exponentially many states. On the right-hand side we have only linearly many states. Yeah, so this reduction can take, you can reduce things quite drastically. A nicer example, to my opinion, is even the example of the bakery algorithm. So the bakery algorithm is an algorithm developed for mutual exclusion by Leslie Lamport. And the idea is the following. It's like on Saturday morning you go to a bakery shop, it's very occupied. When is your turn? Your turn is you have to get a ticket when you enter the shop. And this ticket gives you a number. And when the number is on the screen, I guess you all know this scenario, it's your turn to be served. Good, so that's the idea here as well. So that's why it's called the bakery algorithm. So we have, just to show you this for 2 processes, you can easily generalize it for more. There are 2 additional shared variables, x1 and x2. And x1 is basically the ticket of process 1 when it enters the shop. x2 is the ticket of process 2 when it enters the shop. Okay? Good. If P1 and P2 are waiting, the following scenarios can happen. Well, if x1 is a lower number than x2, then P1 enters the critical section. P1 is the next person to be served. If it's the other way around, then P2 is the next person to be served. That 2 people get the same number, this is unavoidable. This cannot happen. Yeah? So we assume this is an ideal machine. You will not have the same number. And now the bakery algorithm by Lamport, it's a bit simplified, but it's basically the core of it, says the following. This is the algorithm for P1. It's an infinite loop because if you leave the bakery shop, you have forgotten something and you go back because you want to buy something else. Yeah? So this is infinite loop. You first do something non-critical because you're chatting with your neighbor, you're not doing something interesting. At some point you say, well, I want to have my ticket. So what's your ticket? Your ticket is 1 larger than the ticket of your opponent in the bakery shop. Then you wait until your number is smaller than the one of the neighbor, yeah? Or the neighbor has basically left the shop. x2 equals 0. If this is the case, you will be served, which means you enter the critical section. If you are finished by being served, you set your local variable to 0, such that your opponent, right, has the chance to being served because this disjunct becomes then true. Good. Symmetrically, it's P2, and initially x1 and x2 equal 0. What is the size of the state space of this protocol? I would say unbounded too, yeah, because you can enter the system, the other one is still there, yeah, and that one is being served, but before the other one is being served, the other one enters the shop as well and gets the next ticket. Yeah, so we start with 0, 0, the first one gets 1, the other one gets 2. Then the number 1 is served first, but then immediately enters the shop again, so gets number 3. 2 is being served, yeah, leaves the shop, but immediately wants to enter the shop again, gets number 4. Yeah, so this grows unboundedly. So the state space is actually infinite. So this is the program graphs. And this is the state space. Well, it doesn't fit on the slide, so that's why there are many dots here. Yeah, this goes on ad infinitum. And the scenario I just explained to you is that the two counters are 0, 0. Then it becomes 0, 1. Then at some point you can get 2, 1, right? And from 2, 1 you can get 2, 0, and then 2, 3, and so forth. Yeah, so this counter grows unboundedly, so we have to deal with an countably infinite transition system. Good. Okay, this is a run. I'm going to skip this. I think the scenario is basically clear. Now the interesting thing is this is an infinite transition system, but it has a finite bisimulation quotient, provided you're interested in certain properties. I mean, it depends always on the set of atomic propositions that you're interested in. So if the atomic propositions are only, you're in the non-critical section, you're waiting, or in the critical section, which were the atomic propositions we have used so far always for the mutual exclusion algorithms, then actually this is the finite bisimulation quotient, because what's the real relation? The only relation that you really need is whether two things have the same number, 0. This one is 0 and this is strictly positive, or the symmetric one. Here the ordering is that 1 has a higher number than 2, or 2 has a higher number than 1. Yeah? And that's basically all you need to know about the counter. So basically we abstract from the value of the ticket you get. It's not important whether you got 28 and your neighbor has 29. It's only important whether your number is lower or higher than the one of your neighbor. And by means of bisimulation with respect to those atomic propositions, you get this as a quotient. Good. Which means, think about this theorem. You want to prove for the infinitely, the bakery algorithm with an infinite transition system, whether it satisfies a CTL formula or a CTL star formula. We know that T is bisimilar to its quotient. Now we can check the CTL formula on the quotient, and that's trivial because it only has a finitely many states and even less than 10 states. Good. Okay, I think I don't have to recall CTL and CTL star. I basically want to spend the rest of the lecture on this theorem that I put here, and I would like to show why this theorem holds. Good. So what I want to prove is actually, let's ignore C for the moment. I will make a remark about C later, so for the moment just ignore C. I want to prove that strong bisimulation coincides with CTL equivalence and coincides with CTL star equivalence. Good. So the first thing I'm going to show is the following. So basically the proof is as follows, that this relation, which is actually the relation on a single transition system, on the slide this is with the subscript TS, implies CTL star equivalence, and that implies CTL equivalence, and that implies TS. I think in German this is called a Ringbeweis. Yeah? Good. So what's the easy part? Well, this is the easy part. That CTL star equivalence implies CTL equivalence. This is easy because CTL is a subset of CTL star. No. So that's given. Okay, at least one step is given here for free. So let me start with the first step, which is this step. And then we're going to see the second step, which is this step, that CTL equivalence implies strong bisimilarity, or bisimilarity. Good. So 1. So how would you do the proof of 1? Then basically you take two parts. Namely, we have to prove the following. If S1 is bisimilar to S2, this implies for all state formulas in CTL star, S1 satisfies phi if and only if S2 satisfies phi. So this is in CTL star. And we also have to show B. If pi 1 is bisimilar to pi 2, this implies that for all path formulas in CTL star, we have that pi 1 satisfies phi if and only if pi 2 satisfies phi. Good. What do I mean by this? By that I mean the following. Suppose I have pi 1. Intuitively speaking, they are pairwise, state-wise they are bisimilar. So if pi 1 is something of the form S10, S11, S12, S13, etc., then we have pi 2, and that's something of the form 20, 21, 22, 23, etc. I'm saying that those two things are bisimilar if and only if they're state-wise bisimilar. So that means basically for all I have that S1I is bisimilar to S2. Y2 is a 2y, 1, I first number them with the number 1y is the same as 2y. Yeah. So this one is related to that one, that one, that one, that one, etc. That's what I mean by this pi 1, etc. Good. So we have to prove these A and B. So how to prove this is by, the proof is by simultaneous induction. Simultaneous induction on state formulas and so on phi and phi respectively. Good, I'm skipping the standard things like the basis and so on. Let's just look at in an induction step. So an example of an induction step is the following. Let phi be a CTL star state formula for which A holds, and let phi be a CTL path formula for which B holds. Good. And now can we distinguish several cases? So for instance, we can look at the following case, a simple case. Let's for instance look at the case that phi is existentially phi. Good, then it suffices to prove by symmetry that S1 satisfies existentially phi implies S2 satisfies existentially phi. Yeah, so let S1 be bisimilar to S2. Assume S1 satisfies existentially phi. That means that for some path pi 1 from S1, we have that pi 1 satisfies the path formula phi. That's exactly what this formula says. We know by path lifting there is some pi 2 which is a path starting from S2 such that pi 1 is stepwise bisimilar to pi 2. That was the argument I showed you, that if you have S1 that is bisimilar to S2, this one can go to S1 prime, then this one can go to S2 prime, then this one can go to, what is it, S1 double prime, then this one can follow to S2 double prime, and so forth. So we have that if this one has a path, that one needs to be able to, this is pi 1, this is pi 2, then that needs to be able to have this situation. By induction hypothesis on B, yeah, so I'm using this hypothesis here, it follows that pi 2 satisfies phi, but then S2 satisfies existentially phi. The key point here is not, I mean, the proof is really straightforward, but the key point is that you do simultaneous induction over the state formulas and the path formulas. Yeah. And you have to do that because here you would like to prove something for the state formula, but this of course depends on this path formula, and therefore you need to be able to apply this inductive argument to the path formula. And the same is the other way around. So if you look, for instance, at another case, let's say you look at the case phi equals phi 1 until phi 2. Maybe it's good to remember phi is a CTL star formula. So in CTL star you can have path formulas until a path formula. Now if you do a couple of steps of the proof, then basically what you would like to show is that you say let P1 be bisimilar to pi 2. And then you say and pi 1 satisfies this formula. So what does that mean? It basically means the following. Pi 1 satisfies this formula if and only if semantics pi 1 starting from some index j satisfies the second part, and for all I strictly less than j you satisfy the phi 1. Yeah, that's the semantics of the until formula, and now the inductive argument comes into play, because now what you need to see is, okay, I know that pi 1 is bisimilar to pi 2, that's my assumption, but that means that for all k, pi 1 starting from position k is bisimilar to pi 2 starting from position k. Yeah? And that means that now I can apply the inductive argument here, and I can apply the inductive argument there, and then I hope you see that you can complete the proof and show that pi 2 satisfies the until formula as well. Yeah? But the key property is this. Yeah? So that means that if and only if pi 2 satisfies phi 2 and pi 2 satisfies, yeah, for all. and thus phi 2 satisfies phi 1 until phi 2. So what did we show? We showed already this part. Yeah, this part is already shown. This one was easy, and that's what we just have shown by means of this simultaneous induction. What is left is step 2. CTL equivalence implies bisimulation. Okay. The first thing that we need to observe is now sufficient to look at CTL, because CTL star equivalence implies CTL equivalence. We don't have to, let's say, look at the full generality of CTL star. Yeah. Good. What else is important? In this proof, I did not use any assumption about the transition system. Being it finite, being it infinite, being it infinitely branching, be it infinite branching, that does not play any role. So actually this, part 1, holds for any transition system. This part, of course, also holds for any transition system. Where does the restriction to finitely branching come into the play? It comes here, y2. So here we're going to see only for finitely branching transition systems. What is a finitely branching transition system? It simply means that for all states in my transition system, the set of direct successors of S, right, the cardinality of this is finite. Yeah, so I cannot have infinite branching. I can have infinitely many states, but not infinitely branching. Good. So we come to 2. I want to show that if 2 states are CTL equivalent, yeah, this implies that S1 is strong bisimilar on my transition system for S2, and this holds for any finitely branching TS. Good. So what we can do is, of course, we can assume that we have 2 states which are CTL equivalent, but we have to prove this. What do we need to do to prove this? We need to find a bisimulation relation containing the pair S1 and S2. What would be the obvious candidate? The obvious candidate is, well, this is what we know, so why don't we pair all the states for which this is true? Yeah? And then let's see whether we get along with the proof. If not, we maybe have to twist it a bit or tweak it a bit. So let R be a relation that says S1, S2 belongs to S times S, such that S1 is CTL equivalent to S2. Good. It's obvious to see that this is reflexive, transitive, and etc. But we have to prove that this is a bisimulation. Yeah? Proof obligation. Is a bisimulation relation. Good. On TS. Remember that I mentioned we defined it originally on 2 transition systems. Here we consider a single one. So this is the version that we need for the single one. On TS. Good. So this works as follows. A. First, as S1 is CTL equivalent to S2, it holds that S1 satisfies A for some atomic proposition A if and only if S2 satisfies A for all A in AP, because I can write for any atomic proposition a formula down for this atomic proposition. Hence L1 of L of S1 equals L of S2. They need to be labeled with the same atomic propositions. Good, that's the first condition. That's the easy one. Now we have to prove the following. That was the simulation condition that says, okay, if S1 can move to S1 prime, then S2 can mimic this, so there needs to be an S2 prime such that S2 can mimic this to S2 prime. Yeah. So here I should have written down, of course, let S1, S2 be in the relation, right? Then S2 can move this and the successive things are related. We're going to show this by contraposition. So that's the following. We're going to say let S1, S2 in R, as we had before, and I'm going to consider the transition from S1 to S1 prime, and we're going to assume that there is no successor of S2 which is related by R to S1 prime. Yeah, so this is the situation. S1 has a direct successor S1 prime. S2 may have several direct successors. Yeah. How many? Finitely many, because it's finitely branching. But none of these is bisimilar to, is not in R with respect to S1 prime. That's the assumption. So what do we know? What's the situation? We have S1 having a direct successor S1 prime. We have S2, which maybe has a couple of successors. Let's call them whatever, T1, T2, etc. But we know that there are finitely many. That means K is finite here. So since Ts is finitely branching, post S2 is finite, say post S2 is T1 up to Tk. Now the assumption was, by assumption, Tj is not related to S1, so that means that S1 prime, and Tj are not in the relation for any j at most k. That was the assumption. None of those successor states are related to S1. All these relations, they are not there. So that's what we can use now. But now it follows from the definition of R that for some CTL formula let's call this formula psi j, it holds that S1 prime satisfies psi j, but T j does not satisfy psi j. Yeah. They are not in a relation, so there needs to be at least one CTL formula that can distinguish between the two states. Consider now the formula phi, which says there exists next psi 1 and psi k. Yeah, so we have that S1 prime satisfies psi 1, psi k. So S1 satisfies phi. But as Tj phi j for all j, it follows that S2 does not satisfy phi. But then S1, S2 should not be in the relation, and this is a contradiction because our starting point was, let's assume they are in the relation. Yeah, so here we use the finitely branching thing so that we can reason about all direct successors of S2. Why is it needed to have a finitely branching thing? That means that we can build a finite formula like this. Yeah, if there would be infinitely many, this construction would not work anymore because we had a formula which is has infinite size. For the rest, what is important to observe is basically that the only thing we need is a next. I come back to this in a minute. And that concludes the proof of the whole theorem. So let's go back to the theorem. What do we now what did we establish? We established the following: bisimulation, this relation on a transition system, is equivalent to CTL equivalence, and that's equivalent to CTL star equivalence. Yeah. Good. What are the consequences of this theorem for finitely branching TS, right? Because we have seen this last step, this from this to there, it only works for finitely branching. A few remarks about this theorem. First, the remark that I already made in the beginning. We have that CTL is a sublogic from CTL star, so strictly less expressive, but the equivalence induced by this logic is, coinciding with the equivalence induced by CTL star. So despite the fact that this logic is more expressive, it's not able to distinguish states in a better or in a worse way. It can characterize states in the same way as CTL can do. Good. What else? What are the other consequences? Good. So, consequences. So we have seen CTL star is the same, equivalence is the same as CTL star equivalence, despite that CTL star is strictly more expressive. What else is the consequence? The consequence is that if S1 is not bisimilar to S2. So suppose you're giving a transition system, you're asked to say, well, are these two states bisimilar or not? And your argument would be, well, they're not. One way to prove this, if then for some CTL star formula phi, yeah, S1 satisfies phi, but S2 does not satisfy phi. So in order to show that two things are not bisimilar, you give me one CTL formula that holds for one, not for the other, argument done. Okay, now you may say, well, it's not easy to find a CTL star formula because of very rich logic. Yeah, but that we have seen that actually it's the same as saying for some CTL formula. Yeah, S1 satisfies phi, but S2 does not satisfy phi. Yeah. Can I find even a smaller logical fragment such that still this argument holds? Yes, you can, because in the proof we have seen we don't use until. So why don't we get rid of until? Indeed, you can even show there is no until for some CTL minus until formula phi, S1 satisfies phi, but S2 does not satisfy phi. Yeah. So this gives you a very powerful way to prove that two things are not bisimilar. You give me a very tiny logic, a logic CTL without until. So the only things you have are things like true, yeah, you have atomic propositions, things like conjunctions, negation, existential next, yeah, of a state formula, and that's it. Yeah, that's all. So in this logic, if you can find a formula in that logic that can distinguish the two states, your argument, the conclusion of this result is that the two states are not bisimilar. This is a very important result in the literature, in particular also the CTL without until, and this logic actually therefore deserves a special name, and it's called Hennessy-Milner logic. Yeah, it uses a slightly different syntax, but that's basically the same thing. Yeah? And this is known as the Hennessy-Milner theorem. Yeah? Milner unfortunately passed away a couple of years ago, but Matthew Hennessy is still alive and kicking and living in Ireland, and they're well known for this theorem. Good. Any questions so far? Yeah.
You said it's equivalence relation to the process bisimulation relation. How do we know that the process exists? So you define this bisimulation relation on the transition system T and
Yeah.
the process bisimulation relation.
Well, you define this relation, right, as saying, well, two transition systems or basically this relation exists because it's defined as being the union of all R's such that R is a bisimulation on TS, right?
Yeah.
Good. I wrote it down by saying this relation holds if there exists a relation. That's another way of writing down the same thing. Yeah? But that's basically what it is. Yeah? Good. Other questions?
In the second implication from CTL equivalence to bisimulation, we needed the finitely branching property.
Yes.
Isn't this, it's the same case for the implication CTL star equivalence to bisimulation, right?
Yes. Yeah. Yeah. Absolutely. So the direction basically from the logical side to the bisimulation side, that requires this finite branchingness property. And whether you start with CTL or CTL star or even CTL without until, it doesn't really matter. Yeah, and the thing to see that is in the proof. So that was the point I tried to highlight. It's gone. I mean, it's already gone. It was on this board. But I used in the proof this construction that exists next something of the form psi1 blah 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 and psi k, where k was the number of successors of S2. Yeah, and that's what I explicitly used here. Yeah? If this becomes infinite, this proof construction doesn't work. Yeah? Good. We can now finish with a counterexample why it doesn't work for infinitely branching things. Yeah, that's unless there are other questions so far. No. Good. Are there any other consequences I should mention? Well, in particular, what we know is so maybe consequence C. We know that a TS is bisimilar to its quotient. Yeah? That's something we have seen before. So what does that mean in practice? You have a CTL formula or a CTL star formula or a Hennessy-Milner logic formula. You want to check it on this transition system. What you're going to do is you're going to construct this quotient. I didn't tell you how to construct it, but it's similar to minimization of automata. And the algorithm to do that has a complexity which is m log n. N is the number of states. This is the number of transitions. Yeah. So this is the cardinality of the transition relation. Yeah. And that means you can very efficiently, starting from this transition system, you can efficiently compute the quotient. And now thanks to this result, you do the model checking on the quotient. And we know that all results carry over. Yeah? If the model checking result here is negative, here it is negative. If here it's positive, there it's positive. Yeah, yeah, you laugh because there are other abstraction techniques that try to collapse more, and then you don't preserve positive and negative anymore. And then you get things like spurious counterexamples and so forth, because you would like to reduce the state space any further. But that means that you go beyond bisimulations, and you look like things like simulation relations or partial order reduction and so forth. Okay, why doesn't it work for infinitely branching? I mean, I was arguing why the proof construction doesn't work, but now, of course, this doesn't show that this is a kind of general argument. So let's try to see whether we can have a counterexample of an infinitely branching transition system. So, example of an infinitely branching such that S1 is not bisimilar to S2, but S1 is, for instance, CTL equivalent to S2. Good. So we take a set of atomic propositions which is infinite. Then I take subsets of AP, and I have states of the form S1 and S2. This is my state space, together with states of the form TA, where A is a subset of AP. So this gives me infinitely many states. Yeah. Maybe a picture will do. I mean, S1, S2. They are labeled with empty set. And then there are these TA states. So let's call them TA1, TA2, whatever, TA3. And finally, we have the state TAP that contains basically all atomic propositions. The labeling of these states is simply the set A. So the labeling of TA is A. So this is labeled with A1, A2, A3, AP. And the transition system, the structure looks as follows. I have to be careful. S1 has a transition to all those TAs. Except the last one. So this one is not there. For S2, similar, so it has a transition to this one, to that one, to that one, but also to the last one. So here there are many, here there are many. So this one also has a transition to that one, but not to the last one. So post S1 are all the states TA, such that A subset of AP, but A differs from AP, and post S2 are basically all the TAs. Then there are transitions back. Basically, I think from all the states you can go back to the S1. So basically it means that from here I can go back, from here I can go back, from there one I can go back. So we basically have that post TA is the singleton S1. Good. Clearly, S1 is not bisimilar to S2, since S2 has a transition to TAP, and that cannot be mimicked by S1. Simply because there is only one state labeled with AP, and this transition is missing. But S1 is CTL equivalent to S2, as the set of finite of the set of atomic propositions in any CTL formula is finite. And S1 is bisimilar to S2 for any finite subset, let's call it AP prime of AP. So you want a counterexample which has countably many. I have to think about this, but it's a good point. Yeah, I have to think about this because that's not something that I can at the top of my head. No, good question. Yeah. This brings me to the end of this lecture series on model checking. I only want to say a few words about possible further directions. So in the next semester, winter semester 18-19, I'm going to give a course which is called Model Checking of Probabilistic Systems. So there the question is not can we reach a deadlock situation? Is it possible to violate mutual exclusion? But then the question is with which probability do those phenomena happen? Yeah. This is used quite a lot, for instance, in safety analysis. Yeah. I mean, think about autonomous cars and you would like to know what is the probability that some kind of accident happens because of the autonomous software running in a wrong way. So here we will be confronted with logics that are able to express something about probabilities. So for instance, you can express something like with probability at least a half, you can reach a B state via only visiting A state. Yeah. And now I would like to check whether a state satisfies this formula or not. Yeah. How am I going to do this? Yeah. And therefore what we need is techniques from numerical mathematics to solve these kind of things. Yeah. So the way we're going to do this is we're going to solve linear equation systems. Yeah. For more richer models that also have non-determinism, we're going to solve. We're going to do linear programming. Yeah, solving linear inequation systems. If you have models that have parameters, so things like this, you have a state and you can move from that state to that state with probability p squared plus q. You don't know p, you don't know q, right? But I want that my system satisfies this property. Can you synthesize for which p and q the system satisfies these properties? And that means that we have to deal with rational functions. We have to apply satisfiability modulo theory to solve these kind of things. Yeah? So if you think this is cool, then you are welcome to address it. In the other lecture I'm going to give is what is called probabilistic programming. This has not much to do with model checking. You all know object-oriented programming, aspect-oriented programming, functional programming, logical programming. This is programs that can also every now and then flip a coin. Yeah, and then questions arise that they are infinite state. Yeah, so a very simple example is the following example. We have a line, and the line has points. 0, 1, 2, 3, 4, etc. Let's suppose I start somewhere. Let's suppose we start at 10. And now my program does the following. Yeah, while x is larger than 0, then what we do, we're going to flip a coin. Yeah, and we're going to say x minus minus with probability a half, or x plus plus with probability a half. Yeah. So this means in this position, I go here with probability a half, I end up in 9. With probability a half, I end up in 11. Yeah. Question, does this terminate? Be more precise, does it terminate with probability 1? Yeah. Which means termination means we have to hit 0. Yeah. Good. And that means that you have to require proof techniques for programs to show that these programs terminate. How are we going to do this? Yeah. It is a difficult problem. It's undecidable, and it's more undecidable than the halting problem. Yeah, and that's something I want to show in the lecture. Yeah, how much more undecidable it will be. How you can still prove these kind of techniques. So I can assure you this program terminates with probability 1. And I have one other question before I let you go. How many steps does this program need to do on average to terminate? This looks like a silly question because an ordinary program, if it terminates, it needs finitely many steps to terminate, right? Otherwise it doesn't terminate. Right? This terminates with probability 1, but the number of steps to terminate on average is infinite. Good. If you think this is cool, then if you think this isn't cool, then you should go there. Why is this important? This is a very abstract, this is a random walk. A mathematician would immediately say this is a random walk and so on. This is hard, and we know this. Probabilistic programs is nowadays en vogue. Why? Machine learning. Yeah. So there are models like Bayes networks. Yeah, Bayes networks are a simple model used in machine learning. And I will show in the lecture there is a one-to-one correspondence between Bayes networks and probabilistic programs. You can use program verification to analyze Bayes networks. Yeah? And actually in my group we do a lot of research. Marcel in the back is doing research as well on this area on probabilistic programs. Not only those theoretical questions, but also applications towards Bayes networks. How can you prove certain properties about these programs? And that's an enormous challenging field. And if you think this is interesting, then visit this lecture starting in the winter semester. Good, thanks for your attendance. A lot of success with the exam, and hope to see you at some point for whatever reason.